So combining vectors. Suppose we had a box. And suppose we have someone pulling on it at 30 degrees with a force of 10 newtons. And then we have someone pushing down on this side, an angle of 45 degrees with 5 newtons of force. What would be the net force on this box? So how we solve this problem is we have two force vectors. We need to break them up into components. So here's this force vector, has a magnitude of 5 newtons, and we can break this up into a down and a right component. The right component, since it is adjacent to the angle, will be equal to 5 newtons times cosine of 45 degrees. The vertical unit would be equal to the sine, so 5 newtons times sine of 45 degrees. And so the total forces on this vector can be written as 3.5355 newtons to the right, and because it's 45 degrees, it'll be the same number in the y direction, down. We can do similar to the other one. So the magnitude of 10 newtons. And we can break this up into a right component and an up component. Angle would be 30 degrees. So this one would be 10 newtons times cosine of 30 degrees and 10 newtons times sine of 30 degrees. And so we get 8.6603 newtons to the right and 5 newtons up. And now we just have to add these vectors together. So again, I tend to put right and up be positive, and left and down be negative. So I can convert these numbers. So let's look at the horizontal first. Doesn't matter. So the horizontal direction. Horizontal would be these top two numbers. So it'd be a positive 3.5355 newtons plus a positive 8.6603 newtons. And I get 12.1958 newtons. And since it's positive, you can go ahead and say that this is to the right. Now we look at the vertical component. So this is down, so it would be negative 3.5355 newtons, plus up is positive, so we plug in 5. So that would equal 8.5355 newtons. No, it wouldn't, because it's a negative. It would equal 1.4645 newtons. This number is positive, so it would be in the up direction. So these are our vertical and horizontal components. So we can make a triangle with it. So we have a horizontal component to the right. That's 1.4645 newtons. And at the head of this, so this is called the tail and this is called the head, we add the up component to the head here, connecting the arrows so it follows. And I wrote this backwards. The horizontal is 12.1958 newtons. The vertical is 1.4645 newtons. And to find the resulting, we can connect the tail here to the head here, which forms an angle. And here would be our magnitude. So our magnitude is equal to the square root of the component squared, the sum of the square components. So that would be 1.4645 newtons squared plus 12.1958 newtons squared and we get a magnitude or a length of 12.2834 newtons. The angle is equal to the inverse tangent or the arc tangent of opposite. Opposite is for a 1.4645 newtons divided by adjacent 12.1958 newtons. So theta is equal to inverse tangent of opposite divided by adjacent, whereas the magnitude F is equal to the square root of adjacent squared plus opposite squared. Making sure your calculator is in degrees always. Some people like resetting the calculators. So always check first that it's correct. And this would be degrees. So, in summary, these two forces, when added together, is equivalent to a single force that has a magnitude of 12.2834 newtons, an angle of 6.8474 degrees. Make sense? Alright, suppose we have 2 ropes. Let's make, I'm gonna wing it. I don't know if this is possible yet. Let's say that we have 2 ropes holding up a box. So it has a mass m. So and times g, where g is the acceleration due to gravity. Suppose the max force that each rope can handle is 1,000 newtons. What is the largest mass that can be supported by the ropes in this configuration? Nicole, would you mind running to the printer, grabbing all the stuff? It's probably on the table. So we're solving for m. How would you think we'd solve this? Well, that's what we have to find. It's math. So what's something we should know about this problem? Well, that the rope breaks if it's greater than 1,000. What else can we gather from this problem? Is the box moving? What does that tell you? If box is moving, sum of forces, 0 newtons. So let's break all these up into components. Let's look at all 4. I'm gonna call this. We usually call this tension when it's a rope. So I'll call this tension force 1, and this the tension force 2. It'll be in this direction. So let's look at the horizontal components. So for T1, or let's just analyze T1 first. So T1, let's just 1 foot up. The rest is for IPC. So we have this T1 force. It's going to have a vertical component and a horizontal component with an angle of 35 degrees. So the vertical component would be equal to T1 times cosine of 35 degrees. The horizontal component would be equal to T1 times sine of 35 degrees. T2 has a horizontal and vertical component at 70 degrees. So the horizontal component would be cosine of 70 degrees. The vertical component, you mind closing the door, Nicole? Opposite of the angle, so sine of 70 degrees. So now let's look at the horizontal components. We have this horizontal component, T1 times sine of 35 degrees, and this would be to the left. We have this horizontal component, T2 times cosine of 70 degrees, and it'll be to the right. Looking at the vertical component, we have mg pointing downward. We have T1 cosine of 35 degrees pointing upward, and T2 times sine of 70 degrees pointing upward. So if the sum of forces is equal to 0, that means that the horizontal forces have to sum. So write that first. If the net force is 0, then all components must be 0. So again, letting up and right be positive, and down and left be negative, we can come up with a system of equations. T1, so this would be negative, so negative T1 sine of 35 degrees plus T2 times cosine of 70 degrees has to equal 0 newtons. Negative mg plus T1 cosine of 35 degrees plus T2 sine of 70 degrees has to equal 0. So we have two equations, and we have three unknowns, T1, T2, and M. There's not enough information to solve this, as it is right now. We have two cases, though. Case 1, T1 equals 1,000 newtons. So let me go ahead and solve for T2. So using this equation to solve for T2, add this over here. So T2 times cosine of 70 degrees has to equal T1 times sine of 35 degrees. Dividing by cosine of 70 degrees, we see that T2 is equal to T1 sine of 35 degrees divided by cosine of 70 degrees. So if T1 is equal to 1,000, we can plug that in. T2 times must be equal to 1,000 newtons times sine of 35 degrees divided by cosine of 70 degrees. And we see that T2 is equal to 1,677 newtons. Is this possible? No. T2 would have broken a long time ago before T1 is equal to 1,000. Right? So this case must be false. Because T2 would have broken. Case 2, T2 is equal to 1,000 newtons. So we can pull down that equation. T2 times cosine of 70 degrees equals T1 times sine of 35 degrees. Solving for T1, T1 would equal T2 cosine of 70 degrees divided by sine of 35 degrees. So if T2 was 1,000, we can plug that in. And we can see the force on T1 is 596.294 newtons. This is possible. So this second rope is at its breaking point. And this rope still has a whole lot more and doesn't break. So this case is the case that's possible. The other case is impossible because the other rope would have broken before T1 reaches there. So now we know that T1 has to equal 596.294 newtons, and T2 is at its breaking point of 1,000 newtons. Now we can solve for mg. So moving this over, that'll be T1 times cosine of 35 degrees plus T2 sine of 70 degrees is equal to mg. Switching the equal signs around and dividing by g, we see that the mass is equal to T1 cosine of 35 degrees plus T2 sine of 70 degrees divided by g. And we can plug our numbers into it. T1 is equal to 596.294 newtons times cosine of 35 degrees plus 1,000 newtons times sine of 70 degrees, all divided by 9.8 meters per second squared. Oh, by the way, if you haven't figured out, two-dimensional has a ton of math in it. Expect whole pages to be written for one problem. This is also the simple cases. So we get 145.73 kilograms. So if you wanted to actually test this, get two similar ropes, hang it up on a hook, and start putting increasing weight until the rope breaks. That will tell you, and then you could just divide by G to get how much newtons, you want to measure in kilograms, how many newtons of force that rope can support. And you can figure out optimal angles and support something, it can support something like this. If you're curious, so if this was 145.73 newtons, I can multiply that by 9.8, and we can see that we get 1,428.15 newtons.
Excuse me, teachers, for a quick interruption. Could I get you to get caught up on your attendance first and second period, please? Thank you.
So we can make these ropes hold up something past their breaking point by just doubling them up and moving it over at different angles. Does that make sense, or was that too complicated? Again, I usually spend like 2 full weeks on this. Technically, they can start coming back next week. But if they want to wait till the last minute, they're forced to come back after the 19th. Let's see. So, if you ever want to become an engineer, this is what they actually do. Is they actually will figure out total force. So there are certain tolerances. They won't use the breaking point. What they would do is they'll do like 70% of the breaking point. They'll assume but they'll plug in the same number. They'll just like, instead of doing 1,000 newtons, they'll analyze it with 700 newtons, so it never gets anywhere close. They also like to pretend everything can rotate and use torques to analyze it, not just that. In which case, they do the sum of torques is equal to 0. So, for example, let's say that we have a beam here and a rope attached here, and this rope at that angle of theta, so there's going to be a tension force. And then we have an object at the end with a mass of m. So this tension force is going to want to pull this rod upward and make it rotate around this pivot point. This mass is going to want to push it down. Recall that for torques, I'm doing that water. Yeah, for torques, only the perpendicular component counts toward torque. So this tension vector, an angle of theta, has two components, a component that's horizontal and a vertical component. So if we could draw an imaginary line here, this imaginary line is horizontal, so only the vertical component will contribute to torque. So the perpendicular component is the vertical component, of t. And so we have a t here, so the perpendicular component is equal to t, it'd be opposite, so we use the sine of theta. And let's let this have a radius of r. So the torques, there are two torques. We have r times t sine of theta, and that would be making it want to rotate counterclockwise. And we also have r times mg, which wants to make it rotate clockwise. Counterclockwise and clockwise. It doesn't matter what you set. Let's solve for m. So I like setting whatever variable has the term I'm solving for. I like to set that direction to positive. So I'll let clockwise be positive, counterclockwise be negative. So the sum of torques equals 0 because it's not rotating. So r times mg is equal to, or minus, so I'd let this be negative, minus rt sine of theta, and that equals 0. So r times mg is equal to rt sine of theta. Notice that since they're at the both same r distance, the r's cancel out. And then we can divide by g. And see that the total mass we can support will be the maximum. So the maximum mass we can support will be tension, the max tension times sine whatever angle is that divided by g. So if you're given a max tension, you can plug it into this thing. We can also do another analysis. So let me pull this out over here. Mg is equal to t sine of theta. Let's say that you knew the mass and you knew the tension force required. We can, but you want to figure out an optimal angle. You can divide t on both sides. Mg divided by t is equal to sine of theta. To get the inverse, to find theta, we would take the inverse sine on both sides, which causes the sine to cancel out, telling us that theta would be equal to the inverse sine of mg divided by t. In this case, the r cancels out, and we're really just looking at the vertical component. So even though I analyzed this using rotational mechanics, the linear mechanics, it worked out to be the exact same. But that's only because the forces were applied to the same point. If this was moved over to here, you would have to keep r in. It'd be some percentage of the distance. But and it wouldn't come out to be the same as linear. So, just to recap, we have hypotenuse, we have adjacent and opposite, or we can have a triangle where theta is here, in which case this would be opposite, this would be adjacent, this would be hypotenuse. Or we can have something like this, theta, where this would be opposite, this would be adjacent, this would be hypotenuse, or any other way of rotating it. Hypotenuse, or magnitude, would be equal to the square root of adjacent squared plus opposite squared. And the angle, theta, would equal the inverse tangent of opposite over adjacent. We also have the fact that adjacent would be equal to hypotenuse times cosine of theta, and opposite equals hypotenuse times sine of theta. And the angle that would be it. So basically that's all we do is use these formulas to analyze them. We could also use theta is equal to the inverse sine of opposite over hypotenuse. Or in any other version. I think that's mostly it. Next week, unless you're struggling on how to do this, we will actually move into kinematics in 2 dimensions. The path a basketball takes as you throw it. I think that's it for today, though. If you're struggling, let me know. I'll go back and reteach things.